Hello everyone, can you hear me? Last lecture. Okay, good. Okay. So let's see. Yeah, I'm it's a bit sad. I will miss you. Yeah, it has been really nice to yeah to have these lectures. Okay, so today we will keep talking about ray marching or sphere tracing, right? So yeah, can you see my screen? I'm sharing my screen. Okay, good. Okay, so we were talking about this different approach to for computer graphics, right? I mean, we've discussed many different topics, right? And but the last one was this strategy of ray marching or sphere tracing, and we were saying that this is in particular this is very useful when you have a certain type of geometry that is probably not created or not represented by triangles, but you have like surfaces that are basically represented by implicit functions or like sign distance functions, right? And so in those cases, sphere tracing is very convenient. But in some other cases, even if you are using very simple objects like spheres or cones or torus, for example, this is also very convenient and it's kind of cheap. Okay, so in particular, okay, so this is basically what we said the other day, right? So you have a surface that is represented by a function, and the way you compute this is just by making your ray like walking right in the direction of the basically on the same in its own direction, right? And what you need is to on every cycle you need to compute the closest point from your ray origin to any point on any surface on your scene, right? So in this case we have two surfaces, and you obviously choose the one that is closest, and just choose the one that is closest, and you create like different spheres because there's absolutely nothing inside each of these spheres, and just keep walking until you get into a specific threshold distance. So another way to represent these functions is by something like this. So a sign distance function is in the end it's just like a tiny machine, right? That you just plug numbers and it will say it will return a distance, either positive or negative. And basically, if the distance is very close to zero or is actually zero, it means that you are basically on the surface. So this type of functions are very common in general in computer graphics. So one of the most common methods for surface reconstruction, it's called Poisson reconstruction, and Poisson reconstruction actually use this type of approach. So for example, imagine you're doing a 3D scanning of something. So you have a laser and you're just shooting a laser into some structure, right? And in the end you get a point cloud of just points in space, right? So there's this technique of Poisson reconstruction that basically will take all those points, and if you have normals for all those points, and they will basically create a sophisticated function that represents a surface, right? With this thing of it will represent a signed distance surface, right? Yes, okay. So, and we were saying, give me a second. Let me show you something. And we were saying that this is in particularly helpful for complex geometry that is sometimes even could be almost impossible to represent with other techniques, for example with triangles, such as fractals, right? So I mean, this is another video I wanted to show you. So again, fractals are the geometry of a fractal in 3D. It could be incredibly complicated, and as if you know a little bit about fractals, basically when you're zooming into a fractal, the same pattern basically will repeat, right? So if it's something super intricate, once you're getting like closer and closer and closer to those surfaces, you're not going to see like the triangles or the pixels, right? You will just keep seeing a super complicated, a super sophisticated surface that has the same patterns, right? So this type of geometry, as we said, it would be crazy to create triangles with this, and but it looks actually very cool, right? So for example, this is the work of an artist. His name is Julius Horthus. I don't know if I am pronouncing correctly. So he has a channel in which he's basically posting all his art, and it's absolutely amazing. It's really, 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 really nice. And again, this is very similar to what you see in Guardians of the Galaxy, right? Okay, so the thing is, using a ray marching algorithm or a sphere tracing algorithm is not always or is not exclusively for sign distance functions. You can also use it for simple geometry elements. So simple geometry, we refer to spheres, cones, boxes, and torus and things like that, right? So let's talk about the torus in particular. There's one way to ray trace a torus. You can directly compute the intersection between the ray and the torus. If you have tried that, it's not a simple task. It's a bit complicated, right? So another way to do it is by ray marching, right, the torus, or sphere tracing the torus. And you have basically two options for that. One option is to create the implicit function to describe the torus as a sign distance surface or a sign distance function. But the other way is to analyze the geometry, or basically compute the closest points, but with vectors, right? Instead of using implicit equations. So that is what I want to show you today. Okay, so give me a second because someone is asking, could you explain how fractals are accomplished through ray marching? Okay, so the thing is, what you have when you are creating fractals, what you get from your equations is basically a super sophisticated function that is determining the surface of that fractal, right? So if you're using ray marching, let's imagine that you have a single function that is representing a single fractal surface, okay? So you just compute the distance from your point, from the origin of your ray, to that surface. That again is represented by a signed distance function. So it will tell you a distance, either positive or negative, right? And that's it, right? Remember, you basically compute the closest point. If that distance is larger than your threshold, right? Now you need to create a sphere, and then you make your ray basically travel from the original starting point, right, in the same direction now on the border of that surface, and you just keep walking until you get into a specific distance that is very small, right? Again, if it's smaller than your threshold, and then you consider, okay, that is an intersection, and I just compute the color, right? Yeah, exactly. So the surfaces are represented by SDF. Exactly. Yeah. I mean, fractals are complex. I mean, we could maybe cover maybe two entire lectures talking about fractals, right? So we don't have time to go deep in fractals, but it's something that if you are interested in that, you could just go and yeah, make some experiments. There's a lot of information out there. There's a very cool software to generate fractals that is actually uses sphere tracing. It's called, I need to remember, I think it's called Mandelbulber. I think it's Mandelbulber 3D. So yeah, I think it's like that. I will, so I think it's like this, Mandelbulber. I'm not sure. I think so. Yeah, the thing is, fractals were discovered by a French computer scientist called Benoit Mandelbrot. And so yeah, so that's why like the Mandel is kind of like referring to the last name of this guy. And okay, good. So let's talk about again ray marching is simple geometry. In this case, ray marching a torus, but we're not going to use implicit surfaces or implicit equations. We will use vectors, right? Vectors are always there in computer graphics. So let's analyze the problem. So we have a ray. We have the way we describe a ray is by a ray origin, right? Basically the initial position of my ray. And we have a ray direction, right? And then we need to describe the torus, right? So what do I need to describe a torus? We need a radius 1, right? Which is basically the big one, the bigger radius. And a radius 2, which is the small one. Do you agree? What else do I need to describe the torus? What do you think? So two radius, two radii, and what else? A position, right? Yes, the center, exactly, the position. And also, in particular, for computing this method in particular, we will need the Taurus normal. So imagine the Taurus normal as the fact that the torus is kind of like a planar shape. I mean, it's not planar, right? It's obviously 3D. But the middle of the torus is basically describing a surface, or it can describe a plane, right? So if this torus is basically rotated, right, in the 3D, that rotation can be described by a normal, right? So imagine that in this case, the way we describe a torus, and again, this is something that you could implement in your ray tracing code, and it will look really nice, and it will be somehow easy to code it. And if I don't remember, if I'm not wrong, this is actually part of the bonus part, right? The torus. Okay, so and someone is saying in 2 days. Yeah, I mean, not necessarily for I mean, I guess if you're interested in computer graphics, you might extend your assignments and your ray tracing stuff beyond these lectures, right? Yeah, of course, if you're already finishing your assignment, that is perfectly fine. But yeah, I mean, after the lectures, you can keep going with this. And if you could have in your resume, if you have if in your resume you can say that you can say I wrote a ray tracer, a path tracer from scratch, and you can mention all the cool features that your ray tracing has, and you're really interested in working in computer graphics, in any computer graphics company. This will be really interesting. Actually, yeah, I will probably talk a little bit about that also, if you're interested, a bit about working in VFX companies, which companies are actually like hiring people right now. In particular, Amazon is looking for people specialized in computer graphics, and yeah, there are very cool opportunities right now. Okay, so let's continue. So in this case, we will describe a torus using two radius, right? Two radii, right? And the torus center and the torus normal. Okay. So having that information, the strategy here, because here is just pure geometry and vectors. So instead of just directly computing the closest distance from the ray origin to the torus, we are going to kind of fragmenting the problem. We're going to compute several closest points to each of the geometric components of this torus, if that makes sense. So the first thing we need to do is we need to compute the closest point from the ray origin to the plane in which this torus is basically living, right? Again, the torus has a normal. It means that there is a plane, this is a plane, right, in which you are basically, basically the plane in which this torus lives. And so we need to compute the closest point to this plane. So for any point in the space, computing the closest points to a plane is just saying that you need to compute the projection of this point into the plane. And this is, by the way, something that is also very common in computer graphics, at least in my area, which is geometry processing. We use this many times. We like projecting points into planes. That is very, very common. And I don't know why somehow every time we need it, we just like we are just trying to implement this thing very fast, and we always make mistakes. This is one of this type of like geometric things that sometimes is kind of confusing. Okay, so the first step to compute point P, right? So we need to compute point P. The first step is to compute a vector that in this case I'm calling the vector A, which is basically the position of the ray minus the center of the torus. Okay, so it's this big vector right here. So this is vector A. Then we need to compute this distance k. So what is k? K is the projection of the vector A on the normal of the torus, right? And if you remember, if you're not restricting your vectors to be normalized, taking the dot product between two vectors will give you exactly that, right? So basically the dot product between A and the normal will give you this distance k, okay? So the next step, if I keep drawing everything here, because this image is in 3D and it has perspective, it'll be incredibly difficult to understand what I'm doing here. So let's focus on this area of the image. This is basically a 2D version of what I'm showing here. So this is the plane, right? This is the plane from the torus. This is the torus center. This is the torus normal. This is the vector A. This is the origin of the ray. And this is the 0, 0, 0 of the world, right? Because in the end, right, the torus can be in any position. So basically this point right here represents this cross right here, right? The center of everything. So computing k is basically this, right? K is this distance, which is basically the projection between this vector A onto the normal, okay? So the next step is to compute the normal from the torus times k, right? So it is basically this vector right here. But I'm drawing the vector now in this position because remember, vectors always start in 0, 0, 0, right? So it's somehow like drawing the vectors, for example, here, the way I'm drawing the vector A is not mathematically correct, right? I mean, in computer graphics, we are always like moving our vectors, right? But in terms of the numbers that we have, right, strictly speaking, A should be starting on the center, okay? So in this case, I will get this green guy to the center because this guy is actually starting from the center. And then the next step is I will just subtract the origin of the ray, the position, the ray or origin, minus this vector right here, or this position right here. So let's call this guy B, okay? But again, this vector right here, right, it is starting actually in the 0, 0, 0 of the universe, right? Because vectors start always from 0. So this vector, although I'm drawing the vector here because I'm basically subtracting this position minus this position, this vector actually lives here, okay? And this vector just points to the position that we want to compute, right? To the projection between the projection of the origin of the ray into this plane, right? So in the end, if we were saying that B is equal to ray, right, the origin of the ray, minus the torus times K, well, in the end, that is P, okay? So P is this, okay? Any questions from this? Any questions? Okay, no questions, good. So we computed the first closest point, right? So as I said, the strategy here is computed several closest points, right, to different elements from the torus. So the first is, okay, now I get the closest point into this plane. So now that I am on the plane, I will need to use something, a geometric entity from the torus that is called the medial axis. So have you ever heard about the 3D medial axis before? Do you know what a medial axis is? No? Yeah, this is a very geometry processing language, right? So yeah, unless you have experience on that area, you probably haven't heard of. So the 3D medial axis from a 3D model. Sorry. So a 3D medial axis of a 3D model is basically a geometric representation of the center of that 3D model. So it's also known as topological skeleton. I mean, computer science, computer graphics, we always like to have weird names for things like this. So yeah, imagine in the end that you take the torus and you just decrease the second radius of the torus until you have basically a circle, right? Well, that is basically the medial axis. And it somehow makes sense, like as seeing this as kind of the skeleton of the 3D mesh. So I have two questions for you, two just basic questions. What do you think is the medial axis of a cylinder? And please don't check the following slides because you probably have. Yes, someone is saying line, point. What do you think? It's a line or it's a point? Because yeah, I have another question, right? What is the medial axis of a sphere? Yeah, so in the case of the cylinder, it's a straight line in the middle of the cylinder, right? And in the case of the sphere, it's just a point in the center, right? So it makes sense, right? It's just, again, like the center of the mesh. So when, and this is also very useful for other computer graphics things. In geometry processing, we use this medial axis a lot. And if you think about the medial axis of a, for example, in computer graphics for animation, I don't know if you know how computer characters are animated. Yes, exactly. Someone is already saying. Average Enrique, enjoy it. Thank you. Exactly. Someone is saying bones, right? So the way you animate characters is by constructing a skeleton in the middle of the mesh, and basically you create bones. So one very cool family of algorithms in computer graphics are strategies to take a 3D model. So in general, in a VFX or in an animation company, if you have a 3D model and you need to animate that 3D model, you need to make a process called rigging, which is rigging is the process of creating bones inside your character, right? Imagine that is, I don't know, a dragon or a horse or whatever. So you need to basically create the bones in the middle and define the bones, like how the bones are going to interact with the mesh and things like that. And it's a very, very, very complex thing to do. It's not easy. Usually in an animation company, I don't know, like Pixar or DreamWorks or things like that, from all the artists that they have, some of the art, like among all the artists, the people that is working on the rigging department, they're one of the most valuable people, and they earn a lot of money because it's very hard, and they need a lot of knowledge about art and how objects move and things like that, but also a lot of computer science knowledge, right? So the medial axis help. You can create algorithms, for example, to automatically compute the medial axis for a character, and basically use that information to automatically compute or automatically create bones, and automatically compute what is called the skinning, that is basically how each bone is affecting different parts of the surface. And you can have algorithms that are basically procedurally creating the rigging for 3D models that exist already. It's very complicated. It sounds very complex. It is very complex. There's a lot of people that is working on that area. That is one of the big areas in computer graphics. But a lot of people is making a lot of money with that because it just saves a lot of work, right? So that is very interesting. So 3D medial axis, you can find an enormous amount of things talking about that. But in this case, it's very simple what we need. So now we need to compute from point P the closest point on the medial axis. Okay? So in order to do that, let's assume for a moment that I will just remove the right. It's I will remove the torus. And so we have the center of the torus, we have the medial axis, and computing the closest point, now it's super simple, right? Because everything is just constrained in a plane. So I just need, I just need to compute this vector right here, right? And this distance, I'm already know what distance is just radius 1, right? So if we said that that the vector P minus the center of the torus, we can call it M, right? So imagine that M is this vector right here and it's normalized. Just multiply that vector times the first radius of your torus and you get to this point, right? So the point M is the closest point from P to the medial axis from the torus, right? Very, very easy to compute. Okay, so from there, now it will be incredibly easy to compute now the actual distance from the ray. Because now that we have that point, the point on the medial axis, now you can imagine now this vector that is basically traveling from the ray origin to the M, and that vector will be exactly on the same plane that a cross section from the torus. So imagine that we had the torus again, and we take a knife and we cut, right? We cut with a knife, we cut the torus with a knife exactly on this plane, right? We have a triangle here, and triangles they always create planes. And so the interesting thing about this triangle is that because this vector represents the projection between the ray origin and point P, it means that this vector is basically orthogonal to the plane, right? So this vector right here actually is the same as the normal. It means that this triangle is also orthogonal to the plane. So basically it's kind of like, imagine that this is a triangle, right? So basically this dihedral angle will be 90 degrees and the other opposite dihedral angle will be 90 degrees. Dihedral angle is basically the angle between two planes. So someone is saying, so the shape can be parametrized by a location of the medial axis and like a theta parameter. You don't need a theta, so you don't need to compute any angle or anything like that. So once you have this thing, right? Once you have this vector right here, and again, the thing is this vector is exactly on the same plane that that could be a cross section from the torus. You just compute this distance. So the distance will be, right, the distance between the ray origin and M, so basically this entire vector, minus the radius, the second radius of the torus, and that will be the distance. That's it, right? So that point basically is on the surface of the torus, and is exactly the closest point to the torus. So as you see, it's basically like fragmenting the problem in different stages. So yeah, like segmenting the problem in different geometric entities, because we first computed the closest point to the plane, then the closest point to the medial axis, and then the closest point to the surface. That is basically what we are doing, right? Because from this point to the surface, this is also the closest point, right? I thought torus R1 is the big radius, but not the medial axis. Well, it is the same. So the radius of the medial axis is R1, right? It's torus R1. They're both basically the same because R1 is the bigger radius, right? Astro this sphere kind of what? Might have missed that last lecture, but what is this stopping criteria for any? Oh, we will talk about that, Luis. Yes, we will talk about that. We will talk about when do you stop? Okay, so any questions about this? Any questions on how to compute this distance? It's very straightforward, right? What is R2? R2 is the smaller radius from your torus. So again, remember, to describe a torus, you need four things. You need its position at center, its normal, right? One big radius, which is basically radius 1, right? This is radius 1, and a smaller radius, which is radius 2, right? So radius 2 is basically this radius. Okay? So it is very straightforward. It is very cheap to compute. Okay, so no questions? Good. So remember, the thing is, these type of things, if you just go online and check, oh, intersection between array and a torus, you might find a lot of different options, right? And the thing is, not every option that you can find on in internet is probably the best option in terms of computer graphics, right? So and also you can come up with your own geometric ideas, right? And someone is saying, shouldn't be m times m. What? M times torus 1 plus torus c. Why torus c? No. We are computing the distance, right? So we are computing only this distance. So basically, I'm just taking the distance between the ray origin to m, and I'm subtracting radius 1, right? Zhang? Or maybe I'm not understanding your question, because you're saying, shouldn't m be, oh sorry, you're talking about m should be oh yeah, of course. Again, okay, sorry about that. Remember that in computer graphics, sometimes we omit the addition to the origin. That is correct. So yes, Sang is correct. What I'm saying that that point m is basically uppercase m times, right? Is basically this a normalized vector times the radius 1. But yeah, strictly speaking, I always need to add the origin. But this is very common. It's very common in computer graphics that we just omit the addition to the origin, because this is the type of things that everybody should know about that. But yeah, you're right. If we want to make this like super clear, you're totally right. So I will make that correction. So give me a second. Thank you so much. Yes. So this will be, give me a sec. But again, that is somehow common. So you always remember that when you're dealing with vectors, we always need to add the origin, right? So torus center will be in this case the origin. Okay, good. So no more questions in this thing? Okay. So once you have this, it's now very straightforward to just apply a sphere tracing, right? Because now you have a function that basically computes every time it just computes the closest distance to the torus, right? So we already know how to do this sphere tracing, right? Every time I create a new sphere, now I just move the origin of my ray to the next position. That is basically just my original ray direction times the sphere radius, right? And I will terminate, or I will finish and find my intersection once that distance is just very close. Okay, so let me now show you, just in case you have problems to visualize this in 3D. So we can see, let me just change the color of the sphere, because the torus, because it's everything is purple, so it's maybe not as a good idea to have this color. Give me a second. Okay. So this is basically what is happening, right? So the torus is basically lying on a plane, right? It's lying on a plane. And this is the ray. So as you can see, the projection between this point, the origin, right? The projection to the plane is this guy right here, right? So this line right there is basically the same as the normal, right? Because it's orthogonal. So we are basically computing, or we are kind of computing everything now in a specific plane, and that plane is exactly cutting the torus in this direction, right? And yeah, This is basically the closest point. So if I compute the sphere tracing, I did a quick code to show you. So I have a couple of functions here. I have, can you see the code? The size is good? Is good? Okay. So I have a couple of functions. Let's see one by one. So this function is just projecting the point into the plane, right? It's exactly using the same formulas that I got in my slides. I'm not probably using the same names because I just did this code like very quickly, and I'm probably not using exactly the same name. This is the function that is just computing the distance to the torus. So it basically gets the ray origin, the torus center, the torus normal, and basically radius 1 and radius 2. And again, these are basically the same formulas, probably not the same names, but these are the same formulas. I have another function just because I'm graphically will create spheres for you to see all these tiny spheres. I'm just having this. And then I have, every time I run the code, I will delete any tracing spheres, right? This like blue spheres that I will create. If I modify the scene, I will just delete everything to create new ones. And I define that the ray origin is the position of this object. So this object it's called ray, and this its position is obviously the ray origin at the beginning, and its direction is the ray direction. And then I just have a while do loop, right? So if while my sphere radius is larger than this value right here, so this is my small value, right? This is the, whenever I am like already that close, I will just consider that as the intersection. So that is basically my threshold. And obviously at the beginning, I need to put a very big number to my sphere radius. And I just compute everything, right? I just compute the radius using this distance to torus function. Then I just create the new sphere. I now recompute the ray origin, right? Because again, there's absolutely nothing on that sphere, so I need to just walk my ray. So this is the walking, right? I just take my original direction times the radius of the sphere plus the ray origin, right? I'm adding the origin here, and that's it, right? So that will be it, and I computed. It will take a bit of time in here because it takes time because I'm creating the spheres, right? But like computing this in C++ without any other stuff, it is actually pretty fast. So these are the entire set of spheres that I'm computing, right? Doing this sphere tracing. So this was the first one. So probably the closest point was here. Now it was probably here. And every time, right, it's just going down until it just gets very close until it's just super close to the sphere. Sorry, to the torus. And if I modify the position of this guy, I don't know, I will make it just miss the torus just by little, and you will see that we will have like this. So if I recompute my where is my code? Here. If I recompute everything, it will delete everything, it will create new, and you can get these patterns, right? This is very cool. This is getting very small, but because it's not getting into that threshold in particular, right? It just keep going until it gets close enough. Okay. So, question for you: how do you terminate your first question is, let me just go back to here. How do you compute the normal of at the intersection? Oh, and someone is asking, which set of shapes can be considered the SDF here? The spheres or the torus of both? Okay, good question. None. So here I'm computing a sphere tracing, right? Or I'm using a sphere tracing strategy or ray marching strategy, but I'm not using sign distance functions. I'm using a different strategy. In this case, the strategy I'm using is by using vectors, right, to like decompose and find the closest position to the torus. But no, yeah. So none of these surfaces is a sign distance function. Okay. So yeah. So question for you guys: how do you compute the normal at the intersection point, right? Because in the end, okay, very nice, Enrique. This is very nice. It's a very easy way to get the intersection between a ray and a torus. And someone is saying final ray position minus point on median line. Yes, I hope you didn't see the I hope you didn't see the next slide. So yes, using the last point on the medial axis, right? So remember, every time you are computing this, we are computing the closest point. Eventually, we're computing the closest point to the medial axis, right? So the beauty of that is because it's exactly on the medial axis, it is on the center of the torus. And in that specific cross section in which you're basically computing the closest distance, the intersection minus that position on the middle axis will give you the normal, right? So it's just beautiful, right? You have everything there. You already have the entire information you need to compute your refraction, reflection, or Lean fung or whatever you want. Everything is there. You can compute the intersection and also the normal. Okay. So the other question is, how do you terminate your sphere tracing when there is no intersection? What do you think? And let me see. So if you already have sphere tracing, why do you still need to compute distance to torus? Okay, someone is asking, if you already have sphere tracing, why do you still need to compute distance to torus? Maybe there's a confusion here. You need the distance to torus to do this sphere tracing. So sphere tracing is based on, right, on every iteration. So the first iteration, you need to compute the distance to the torus, and you get, let's assume you get into this point. So now you define that distance as the radius of this sphere, and then you walk your ray through its direction until the border of that sphere, right? And then just compute the distance again, right? So yeah, you need that distance, right? Okay, so give me a sec because you're writing very fast. You already have, okay, I think sphere tracing needs a geometry function. That's what we are providing by doing this. I think sphere tracing. I don't know. I don't understand your question. You still need to move one radius length for normal. Well, yeah, of course. I mean, so the direction, you take the direction of the normal by taking the intersection minus the point on the medial axis, right? And then you just normalize that, right? And you get the normal, of course. What does it mean, last point on the middle axis? Okay, good question. So remember that, give me a second. The strategy that we are doing is, for every iteration, the way we are computing the distance is by constructing all these projections, right? So we first find point P, and then we find point M, and okay? So point M is the point in the medial axis, okay? And again, that we are computing that every time we are doing a new iteration. So the thing here is, on the very last iteration, when the sphere radius is so small that you consider that you're already on the surface, on the that last iteration, you also had to compute the point M, which is basically the point on the medial axis, right? So this is that point M that you computed the last time you computed the sphere, right? So that you basically use that for computing the normal. Okay, so How do you terminate your sphere tracing? Someone, what is your idea? Because the thing is, if there is no intersection, actually my code will just keep going. If I show you my code, if I show you my code again, I mean, this guy is terminating because there is an intersection, right? But if there is no, look at this. This guy will terminate, or is terminating, if the radius of the sphere is less than this value. But if that never happens, if the ray is just not intersecting the torus, this will never happen, right? Okay, so someone says depth. Okay, can you elaborate? What do you mean by depth? I think you're close, but yeah. Sorry, I need to check my cell phone to see the time. So could you elaborate with depth? What do you mean by depth? Because the thing is, we are not have a max depth. Yes, we don't call it depth, but you are actually, the way you are calling it is actually very nice because it's very computer graphics thing. So it's kind of like the depth from the ray, right? So yeah. Someone is saying T max. Yeah, it's basically the same idea. If the D is greater than what we begin with. Yeah, so exactly. I think everybody has the idea. So what we usually do is we define the termination of our algorithm by travel distance. So yeah, it could be called depth, but it is usually called travel distance. So what is travel distance? So imagine that you have your object. In this case, it's a torus, right? But it could be a sphere or a cone or other object. In this case, it's a torus. So you can compute, for example, a bounding sphere. So remember what a bounding box is, right? So a bounding box is just like a box, right, in which you can put your, it's like the minimal box in which you can put your object inside. So a bounding sphere is basically the same. It's just the minimal sphere that will cover your entire object. So a bounding sphere is a sphere that, in the case of a torus, a bounding sphere needs to start exactly on the same center, right? So it will basically on the same center of the torus. And the radius of the bounding sphere will be radius 1 plus radius 2. You agree? So in that sense, right, if you do that, you have a bounding sphere that is basically covering the entire torus, or it can contain the entire torus. So then what you could do is, if you compute the distance from your ray origin to the center of your torus, and you add the radius of the bounding sphere, which is just getting the distance from the ray origin to the center of the torus plus radius 1 and radius 2, that is basically that, right? That is basically the maximum distance you will travel, right? Before intersecting the torus, if you intersect the torus, right? Which means that if you're computing your sphere tracing and you're walking your ray, right? You make your ray travel, and you need to basically to store what is your maximum distance or your travel distance, right? Your total travel distance. So whenever your travel distance is already larger than this distance, for sure you will not get a new intersection with the torus, right? So you already leave the torus behind. So yeah, that is basically what we use to terminate any sphere tracing algorithm. So yeah, it is very straightforward. You just need to compute that distance before, right? So you have the object, you compute the bounding sphere, or you somehow compute the maximum distance in which you could have any possible intersection, and then you just, every time you're iterating, you're comparing both the smallest, right, your smallest distance threshold to see if you already hit something with your travel distance, and if the travel distance is already like larger than the maximum travel distance, and you still have no intersection. That's it. There is no intersection at all. Okay, so how do you know how many objects there are and where? If there are multiple rays, I guess you can pick the largest distance out of all objects as depth. Very good question. No. This maximum travel distance is it needs to be local per object. So if you have a lot of Taurus, right? Remember that usually, I mean, ray tracing, you're iterating for each object, right? So imagine that you're computing a sphere tracing algorithm or a ray marching algorithm using a spatial partition algorithm, right? You're doing acceleration and you have some sort of a spatial partition algorithm. So if you have if you have a three torus or tori, when you have multiple, it's just tori, right? Not torus. Okay, so if you have multiple objects, right, when you're actually computing the intersection between the ray and a specific torus, you need to define a maximal travel distance for that torus in particular. Yeah, otherwise it will be wrong, right? So the maximal travel distance needs to be local for each object, right? And I think we use infinity for Tmax in the assignment. I don't understand what you're asking. I think we use infinity for Tmax in the assignment. Oh, you're saying for the ray tracing assignment. Yes, for that code in particular, for that implementation in particular, Peter Shirley is using infinity as the Tmax. Yes, yeah. Okay, so that's it. Again, I need to I need to talk about this again. I think so far we have maybe roughly and somebody saying clap clap. Thank you so much. Yeah, this is the sad part of having the course online, that I've been with you for 4 months and I don't even know your faces from many of you. Yeah, it's sad, but it has been a pleasure being your professor. Thank you so much. So if you have time and you can go to the Student Evaluation of Teaching survey, that will be very nice. Remember, this is thank you so much. You're amazing. I'm reading all your comments. Yeah. Really. You have no idea how I appreciate your words. And this is important. Let's all turn off your voice chat and say thanks. Oh, if you want. Yeah, I mean, if you want to unmute yourself, that will be,
great class.
Thank you.
Enjoyed it.
Thank you.
Thank you.
Thank you, everybody.
Thank you.
Thank you, everybody. Okay, so I mean, it's not the last time, right? Because we are still seeing each other. So we will have a final review. So I'm deciding to have our final review. I think it's on Monday, December 14, at 1 p.m. Duration, it says undefined, because it will be basically the same structure than our previous reviews for midterms. Basically, as long as you're making questions, I'll be there answering your questions, right? So if it's 1 hour or 2 hours or 3 hours, I have no idea. I have no problem. So really, and it will be recorded, of course. It will be recorded. The last time it was 3 hours and it was recorded. So it was, again, Monday, 1 p.m. Duration undefined until we finish. Good. Okay, and the final exam, it's on December 17, and I think it's Thursday, right? It's Thursday, 7 p.m. Yes, it's Zoom, right? So I'm still not sure if we will use the exactly same format of having open book, because I might have some constraints from the department. So I'm not sure if it will be an open book exam as the midterms. So it will be at 7 p.m. Also, there's only one time slot. This is super important. Only one time slot. So we will not have one time for people in Vancouver and another time for people in other areas, because in the end it's at 7 p.m. right? So it almost doesn't make sense to have the duration for the exam is 2.5 hours. So it just doesn't make any sense to start one exam at 7 p.m. and then another exam at 9 p.m. when the first one is not even finished. So it's only one time slot. Everybody needs to be there at 7 p.m. And remember, you need to get your ID. That is super important. If you somehow have problems with your ID, you need to send me an email before. And yeah, that's it. So thank you again. Thank you so much. So I will see you on Monday 14. Thank you. Bye.